Hello friends, today's question. A solid sphere of radius r and density rho is attached to one end of massless spring of force constant k. The other end of the spring is connected to another solid sphere of radius r and density 3 rho. The complete arrangement is placed in the liquid density 2 rho and is allowed to reach equilibrium. The correct statements is or are. So this can be a single correct or multi-correct answers in this question. And this is a very interesting question because as we are going to solve this, you will find that we can draw the analogy between spring balance system, which is having two weights connected to its ends, and that analogy is going to help to solve this question in much more, we can say, easier way. So first of all, let us draw a rough diagram for it. So we have two spheres. Let us call this as sphere 1, and that is connected with another sphere, and let us call this sphere 2. Sphere 1 is having a density of rho. Sphere 2 is having a density of 3 rho, and the liquid in which they are submerged, it is having a density of 2 rho. The spring constant is given as k. So in this case, we can easily understand that the density of sphere 1 is less than that the density of the liquid, and for sphere 2 it is more than the liquid. Okay, so this is going to help us to find out, or rather we can say draw, in which direction the force is going to happen. So as the density of the liquid is more than the density of the sphere, so the sphere 1 is going to have a net force in the upward direction, whereas in the second case the density of the sphere is more as compared to the density of liquid, so it is going to have a net force in the downward direction. Okay. So let us start with sphere 1. For sphere 1, which you have density of rho. So we can draw a separate figure for sphere 1 also. So this is sphere 1, and it is going to have, you can say, weight, let us suppose W1 in the downward direction, and a buoyant force that will be acting in upward direction, let us suppose that is given as FV1, and from here we can find out what will be the net force acting on this sphere. So we can say weight W1, and it can be written as M into G. Let us call this M1G, and our M1G, and as both are having radius r, so let us say each sphere is having a volume of V0. So this volume is V0 and its volume is also equal to V0, and V0 for sphere 1 will be equal to V0 for sphere 2, and its value will be equal to 4 by 3 pi r cube. So volume of both the spheres will be our 4 by 3 pi r cube. So our M1 will be equal to V0 multiplied by rho and multiplied by G, and we substitute value of our V0. So we get our W1 is equal to 4 by 3 pi r cube multiplied by rho and multiplied by G. Okay. And then we can find out the buoyant force. And let us call this FP1, and FE1 will be equal to the density of the liquid, that is 2 rho, and we have V naught, that is our volume of the sphere 1, and that will be multiplied by G, and we substitute value of our V naught, so we get FV1 will be equal to, this is 2 multiplied by V naught is our 4 by 3 pi r cube, and this comes rho multiplied by G. So the FV1 will be equal to 8 by 3 pi r cube and rho multiplied by G. So now we can find out the net force on the sphere 1. Net force on sphere 1, let us call that as F1, and that will be equal to our FV1 minus W1. So we substitute the values, we get F1 is equal to, we have 8 by 3 minus 4 by 3, and rest of the things will be common to it, that is pi r cube and rho, and we have G, and this comes as 4 by 3 pi r cube rho multiplied by G. So this is the net force on the sphere 1. Similarly, we are going to write all these equations for sphere 2 also. For sphere 2, which is a density of 3 rho. Density of 3 rho. So this is our sphere 2. Downward direction, let us suppose that is W2. Upward we are having FP2, that's the buoyant force. And we can say weight W2 will be equal to M2G, which will be equal to V naught rho multiplied by G, and volume is our same, that is 4 by 3 pi r cube. And its density is 3 rho. Sorry, I missed 3 here. So this is 3 rho. So we get W2 is equal to 3 multiplied by 4 by 3 pi r cube, and we have rho multiplied by G, and our, we can say this comes as 12 by 3 pi r cube and rho and G. So this is our W2. Similarly, we find out the buoyant force, that is FP2. Buoyant force, which is our FP2, and our FP2 will be equal to density of the liquid, that is 2 rho multiplied by the volume of the sphere, that is V naught, and multiplied by G. And we can say substitute the value. V naught is our, this equals to 4 by 3 pi r cube multiplied by rho multiplied by G. So therefore FB2 comes equal to 8 by 3 pi r cube rho multiplied by G. Now we can find out the net force. Net force on sphere 2, let us call it as F2, and we can say that will equal to W2 minus FP2. We substitute the values, and W2 was our 12 by 3 minus 8 by 3, and rest of the things will be common, so this will becomes pi r cube rho multiplied by G, and this is equal to 4 by 3 pi r cube rho multiplied by G. So this was our F2, and let me write F1 also. so that the comparison becomes much more easier. So we have 4 by 3 pi r cube rho multiplied by g. So these are the net forces on the sphere 1 and sphere 2, or rather we can say entire system basically. Okay. And if you see clearly, the value of F1 and F2 are same, but they are acting in opposite direction. So from here we can draw one important conclusion, that the net force have equal in magnitude, or rather we say are equal in magnitude, rather are equal in magnitude but opposite in direction. But opposite in direction. Sorry. But opposite in direction. So normally we have already, you can say, studied the spring balance system. Let me draw something like this. And in the both ends we have connected a weight that is equal to suppose 300 kg. And if we try to find out what will be the reading on this spring balance, we can easily find out that the net reading on the spring balance, or we can say the reading in the spring balance, will be equal to 300 only. Okay. Now the basic, you can say, a simple concept on this is that the spring balance is going to read the amount of the tension in these strings which are connected with these weights. So if I say T is the tension in the ring, under equilibrium the T will be equal to 300. Good. So the spring is going to read as a 300, and in case we have a, you can say, spring and which is also having a single weight of 300, and it is, you can say, anchored with the wall, then the spring balance is also going to read once again the 300. So from here also the value of tension will be T, and T will be equal to 300. This is quite easy example, we have studied many times. So one important conclusion from here we can draw is that one of the weight is going to act as an anchor weight, and that can be of any value. Okay. This weight can also act as anchor weight, and this weight can also act as anchor weight, and other weight rather is going to give us the exact value of the extension in the spring. This is the basic, we can see, if we compare these two figures, we can draw a important conclusion that one is going to as an anchor weight and other value is going to give us the extension in the spring. The same thing is happening in this case also. In this particular question, here also we have a, only difference is that in this question it is in the vertical plane, whereas here it is in the horizontal plane, and our system is connected by a spring. This is mass 1 and mass 2, and net forces are acting in opposite direction like this. So we have F1 here and we have F2 here. So in this case also, one weight is going to as an anchor weight because both forces are equal. F1 and F2 are equal. So we have both forces, or both weights are same. Okay. So therefore we can say that this is same as a spring balance system which is being pulled or having a weight. Which is being pulled, or we can say having a weight, and the value is our 4 by 3 pi r cube rho and g. at both ends. Okay. So if we say T is the tension in the spring, both ends, and the spring balance only reads the tension, and the spring balance only reads the tension. Okay, or we can say the force being exerted, because in this particular force, the force is being exerted. So in the equilibrium, we can easily say that our tension T will be equal to the value of any of the forces, either F1 or F2, F1 and F2. And from here we can write that this will equal to K, and if X is the extension in the string, so this will be coming as 4 by 3 pi r cube, and we have rho multiplied by G. So this gives us that X will be equal to 4 by 3K pi r cube rho multiplied by G. So this is the answer to the first part, which asks that the net elongation in the spring is. So we have that option number A is the correct option for that. We can say option A is correct. So this is an important analogy between the spring system and this particular question that is given to us. And let us come to the B part. And in the B part, it asks for the light sphere whether it is partially submerged or it is completely submerged. So we are going to check whether it is partially submerged or it is, you can say, completely submerged. So we just said that both the spheres are having the volume V01 as well as V02, and that is equal to 4 by 3 pi r cube. So let me write it again, and this is for volume of sphere 1, that is V01, is equal to 4 by 3 pi r cube, and we have volume of sphere 2, which is V02 is equal to 4 by 3 pi r cube. And in this case, it is asked that about whether sphere 1 is submerged completely or not. Okay, so we assume that let sphere 1 is submerged in water, whether it's water or I think it is a liquid to a volume of V1, So it means the sphere 1 is submerged in the liquid for the volume which is equal to V1. And we know that our buoyant force for that we calculated, that is our FB1, is our 2 rho. Now this will be equal to V1 multiplied by G, because only V1 amount of the volume is submerged in the liquid. So let me write here, therefore buoyant force on sphere 1, and let us call this as for the differentiation FB1 prime. And the net downward force will be same because of V naught, which we said is equal to our not net, sorry, we calculated as W1 weight. W1 is our 4/3 pi r cube, or we can say that is right in the form of volume, rho V naught multiplied by G. And we already know that the sphere 2 will be completely submerged because of the relation of its density. So therefore we can say that for sphere 2 we have W2, which we calculated. W2 will be equal to, density is our 3 rho, so this becomes 3 rho V naught multiplied by G, and buoyant force will be same, that is our FP2, and this FP2 will be equal to, which we calculated is our, one second, we calculated, yeah, FP2 is our, you can say 2 rho V naught multiplied by G. So in equilibrium the forces will be balanced, so we can say at equilibrium W1 plus W2 is equal to FP1 prime plus FP2 prime. So let us substitute the values. W1 is our rho V naught G plus W2 is 3 rho V naught G, and we have FP1 prime is our 2 rho V1 G plus FP2 is 2 rho V naught G, and rho cancel out. Similarly our G also cancels out throughout, so we are left with here, this will be coming as our 4 rho V naught, and that will be equal to, we can take, you can say 2 common, and this will be equal to 2 V1 plus V naught, and this 2 cancel with this 2, so we are left with 2 V naught is equal to V1 plus V naught, and this gives us that V1 is equal to 2 V naught minus V naught. So the final solution says that V1 is equal to V naught, and we assumed that the volume of sphere 1 that is submerged is V1, and this V1 is equal to V naught, and the V naught is nothing but the volume which is completely submerged. Okay, so from here we can say that the sphere 1 will be completely submerged. So the options that are given to us, the option number D is the correct option. So you can say option D is correct. Option D is correct. So this completes the question. Thank you.